again. Thank you.
Yeah. Thank you, Yan, for the introduction. Good morning. My name is Xiaojiang James Du. I'm a professor at the Stevens Institute of Technology. Today, I'm gonna present the work that done with my student Haotian Chenglong and my collaborator Qiang. So the title is called "Delay Rack Talk on Your Smart Home," which is a delay-based automation interference attacks. So we all know familiar with smart homes. I'll go quickly. Smart homes we can use for remote monitoring control. You can do voice control, and also they provide data virtualization. Most importantly, they provide home automation. This particular work actually utilizes another work from our group, which is called IoT Phantom Delay Attack. The Phantom Delay Attack work was actually done before this attack, but due to various reasons, it was published later than this one. So it will appear next month in DSN 2022, okay, next month, okay. So I will briefly mention this Phantom Delay Attack, which is a stepping stone for the attacks in this paper, okay. So in the Phantom Delay Attack, what we found is that the timeout detection implemented in the current IoT TCP layers is decoupled from the data protection provided by the TLS layer, okay. And we did the experiment. We found out that actually an attacker could fool both the IoT device as well as the server or cloud platform to believe that a session is still healthy while the attacker is delaying the IoT event message or command message, ranging from tens of seconds up to several hours. We experimented on more than 50 popular IoT devices. Although the integrity is still protected by TLS, okay. So the most important feature of this attack, it does not utilize any implementation vulnerability. It actually is very stealthy, such that it does not cause any alarm from any layer of the IoT protocol. Due to the time reason, I will not be able to talk too much about this attack, but if you're interested, please pay attention to our upcoming presentation, the DSN, and the paper, okay? So again, this is the stepping stone for our work in this paper, okay? So with the delay attack, basically the Phantom delay attack will delay IoT event message or command for ranging, again, from dozens of seconds to even hours, okay? With the delay attack, we found there are two issues. One is called disorder. The other is called inconsistency. I'll explain those issues. So basically, we categorize those IoT systems into three categories for smart homes. For smart home, if the user usually have a bunch of IoT devices, if the user only uses one platform, say SmartThing or Google or Alexa, whatever, one platform, and all the devices using one communication path. This is called a single platform, single path. There's no such problem, okay? Another category is, okay, the user have a bunch of IoT devices at home, and he still only uses one platform. However, there are different devices. There are Wi-Fi devices directly connect to Wi-Fi router. There's Zigbee, Z-Wave, and Bluetooth, and also Google has the chained protocol. They connect to a hub first, and then hub connect to the wireless router, and then going up. So those are, we refer to multi-path scenario. In this case, the problem is the order of the messages may not be preserved. Let me give you a simple example. Device A generated an event, like a motion event first, and then device B, say, generated another event later. However, if the delay attack delay this link, then the event 1 actually will arrive the platform later. Okay, so basically this changes the order of the message. Okay. The third case is the user, which is more often. I'll show you the survey. User uses multiple IoT platforms at home, including, for example, Samsung SmartThings, Alexa, Apple, and so on, IFTTT. So this is called a multi-platform. And those scenarios, there are not only the order issue, but also the inconsistency issue. I'll just explain the inconsistency issue to you, which is very straightforward. So look at this example. I have a Wemo smart plug. I turn it on, okay? And it will send a state update to the cloud. So the Wemo cloud will show it's on now. But if I launch an attack to delay any link here, then the status on will be delayed, and the smart SIM platform will not receive the on status. It was still showing the plug is off. So basically, even though the plug right now is on, this is showing on, this is showing off. So two different platforms managing the same device showing different status. This is what we call it consistency issue. So those are the two main issues that enabled the attacks that we present in the paper. Okay. So basically, based on those discoveries, let me first talk about this. So we did a user study through Amazon Mechanical Turk. So the purpose is to find out the real deployment in real smart homes, okay? Including IoT devices, what platform they use, and automation apps, and so on. So we already did that, and we found out from about 85 users that most users do use multiple platforms, okay? So about 62% of users use multiple platforms. And about 20% use a single platform, but different passes, like they have Wi-Fi device, they have ZigBee, Z-Wave, and so on, okay? So as you can see, they add together, like more than 80% user use either multi-pass or multi-platform, which could have the attack that I'm gonna talk about, okay? So this just shows you for the multi-platforms, like most still use 2, and like some use 3, and about 10% use 4 and more, okay? All right. So again, with this, there are two main reasons. One is the phantom delay attack, which we published in another paper, and the other reason is the multi-pass or multi-platform. We find out that there are those, what we so-called delay-based automation interference attack. In short, we call it DAI attack. There are some important difference from the cross-rule interference. I don't have time to explain that right now. Okay, so but if you're interested, you can ask me. So let me give you an example. I'll use this example. Okay, so the user has two platforms, A and B. Each platform there's one rule. Let's say this is rule 1. Rule 1 is when the user leaves home, he set the home mode to be away, and then when he drives car away, and the rule will check. This is a trigger. This is a condition. If the user drive away, it will automatically close the garage door. This is the rule 1. Rule 2 is when on a different platform, when the garage door is closed, and if the user is away, I'm gonna also make sure the front door is locked. Okay, so those are two different rules running on different platforms. So what the attack could happen is the attacker could delay the user away message on platform B. Okay. So the user away message was not sent to platform B, okay? And then platform B will check the condition, it does not satisfy. It will not lock the front door, which means when the user left the home, the front door is left open, okay? Could be left open. So that's one example. In this research, we did a systematic study of the DAI attack, and we used some formulation, and we categorized those DAI attacks into 7 categories. Summarized in this table and in the paper. Unfortunately, I don't have time to explain each one in very detail. So basically, we look at because as you know, for the home automation rules, typically use the trigger condition action, triplet, and based on those combination, whether they're overlapping, whether they're conflicting, and so on, we categorize into 7 categories. And the main issue being explored are the 2 issues I mentioned, inconsistency and disorder, and sometimes directly from the delay. Like the attacker can delay a command sent to the IoT device, like lock the door or send the fire alarm, stuff like that, okay? So the consequences could be either some wanted action being canceled out, not executed, or there could be unwanted chained execution, or there could be infinite loop, or like it could be some 2 action usually should be A happen first, B happen second, but due to the attack, the 2 action could have different orders. So I will explain like 3 in details. Okay, again, I don't have time to go through each one. Okay. So let's look at some example in detail. This is one of them called the condition overlapping attack. I'll start with the example and then summarize the attack. Okay. So in this example, again, there are two platforms. The user uses two platforms. Platform A, there's a rule says when motion detected either in bathroom or in the house, and if the user is at home, turn off the camera for like a privacy issue, for privacy reason. The other rule running on platform B is when there's motion detected in the house, and if the user away, then there's something wrong, right? Then I should like send an alarm and then notify user and so on, or send the security video to either the user or the security company. So those are the two rules. What attack could happen is when the user left the home, the attacker could delay the user away message that's sent to platform A. So in this case, on platform A, on the cloud, it's still showing, or local server, it's still showing user status at home. So it will shut down the camera, and which will prevent the second rule on platform B from executing. And if there's some burglar or intruder get in, then it will not be captured by the camera. So that's the condition overlapping attack. And this kind of attack would not happen in the normal situation because, as you can see, they have the same trigger, they have a different condition. If they are on the same platform, it should not happen both at the same time, okay? However, if they're running on the different platform, and also if there's a delay attack, then this could happen, okay? So I'm gonna skip the summarizing, okay? So let me go to the next example. The other example I want to present to you is called action disordering attack. In this case, I see I only have 3 minutes left. I'll skip this one. I'll talk about the next one, okay? Next one is a little bit more interesting. So this is called condition enabling attack. In this case, there are still two rules. One rule is the user setup when he come back home. And so he first of all entered the house, and then the front door will be locked, closed. And then the home was in away mode. Then the rule will, set the home to the home mode and close garage door, say that's the evening, okay? And the other rule is running on a different platform. It's called when the user leaves the home, it will be used. It's when after the user left at home and the front door closed, and it was in the home mode, and then it will open the garage so the user can drive the car out and so on. Okay. So what could happen is, say when the owner is back home, and again the home was set away mode, then both these two rules will be triggered because this happened. Okay. The attack happens is the attacker could delay the front door close event to platform B. So this has been delayed. It's not executed immediately. This is being executed and it's set to the home mode. And it delay like say 20 seconds or 60 seconds and then release it, okay? And then when the rule 3 received the delayed door open message, you'll run this rule, and the home mode already is set to home, and then it will open the garage. So what happens is when after the user come home during night, the garage door will left open. So that's a safety issue. Okay. I'm running out of time, so I'm going to go fast. So we evaluated the DAI attack using two real smart home testbed. Those are the topology, the configuration of testbed. With those numbers are representing different IoT device. We bought a commercial device. Okay. For the two testbed, we use a total of 55 IoT devices connecting to 6 cloud-based platforms, including SmartThings, Amazon Alexa, Wemo, and so on, and 2 local platforms, including Apple, HomeKit, and Philips Hue. And we installed a total of 36 automation rules. Those rules are obtained from the official App Store and from existing papers, IoT papers, or from the existing IoT forums. So those are not like we randomly made up those rules, okay? Okay, so those are part of the rules. Again, I don't have time to go through it, sorry. So we evaluated several things. First, we measured the actual delay that could be caused for different kind of DAI attack. Those are different attack type. And those are what kind of like a IoT event or command being delayed, including like a motion active event, door close event, user away mode set, and so on, okay? And this tells you, what channel to delay it. We implement all those, okay? And those are the delay range, depend on several factors. So anyway, so the delay ranges from 10 seconds up to like 600 seconds. And for the Apple, right now, their implementation, if there's event being sent to the local server, they don't send acknowledgement. So for this case, you can delay for as long as you want. I mean, so it could be tested like up to 40 minutes or even longer. Okay. And we validated all the 7 categories of DAI attack in our testbed. With one experiment is without attack, everything runs normal. Okay, so like the lock is supposed to be locked, it got locked. The garage door got locked. And if there's attack, then things could happen, like the garage door is not locked, or the outlet is supposed to be turned on, but turned off after like 2 seconds, the heater turned on, which messed up what the user wanted. And in this case, the camera turned on after like over 500 seconds. This is because of the delay attack. Okay, it's supposed to be turned on like immediately. So anyway, we validated all the DAI attacks and all being validated. The other experiment we did is we also measured the attack opportunities and the success rate over a week. And this is the summary. For some of the attacks, the success rate is pretty high, but some of them are not like always you can have the attack. Again, it depends on the configuration, the user activity, and so on. And most importantly, so for some of the attacks, you need the delay to be like long enough, like 20 seconds or 15 seconds sometimes, so such that all the conditions are satisfied. Okay, so not all are that high success rate. Okay, but over the time, even with 50%, once in a while, the attacker will have an opportunity to launch the attack. Okay. Okay, so I think I'm almost done. So this paper mainly presented the new set of attacks on almost all the IoT devices we tested. Well, all the devices we tested have this vulnerability, but we did not test all the IoT devices because there's tens of thousands. Okay. So we proposed some simple preliminary possible countermeasurement, like from the user side. If possible, the user could isolate their IoT using a different Wi-Fi network from other users that share like the same Wi-Fi network. From the vendor side, they could revise the IoT protocol such that reduce the keep alive time and the timeout limit, so to reduce the attack window. And from the researcher point of view like us, we could think about what kind of approach we can use to detect the potential conflict in automation rules. Again, those automation rules, if you look at them, you don't see any problem. But because delay attack and the multi-pass, multi-platform, that could be those serious problems. Okay, so let me summarize that. So again, okay, we disclosed this vulnerability to a number of IoT vendors, including Google, Apple, SimpliSafe, Ring, and so on. And several companies acknowledged the problem. Like Google, they awarded us $500, and SimpliSafe and Ring, they acknowledged they tested themselves, and they found that they do have this problem, and they said they're going to improve their protocol. Okay, so let me summarize my talk. Okay, so basically we utilized a primitive, which is the Fenton delay attack, which is our another paper, which is a stepping stone, based on stepping stone, and based on multi-pass, multi-platform, we found their disorder and inconsistency issue. And based on that, we found that there's a family of new attacks, which called the DAI attack on automation rule, which could cause serious consequences on smart homes, including door opening, fires, and so on. And we evaluated on 2 real-world test bed. We proposed some simple preliminary countermeasurement. That's all. Thank you.
Yes. So thanks, Xiaojiang. There's one question from online, like Kushal Kumar asked, are all the categories of attacks observed in all platforms, for example, Google HomeKit? Have you identified any devices that are resistant to these attacks?
Again, we tested like 50 different devices. For the devices we tested, they are vulnerable to those attacks, but I don't want to say it works for every device. I'm not 100% sure. There could be exceptions. Yeah, again, there's tens of thousands IoT devices. So, but based on the popular device we tested, they all worked. Yeah.
Hi, thanks for the talk. Chenglong from RSU. I have a question about, can you talk more about how you implement the attack? Do you send jamming signals? And how long the delay, the attack should be?
Okay,
Yeah.
okay. So this basically is the question for the other paper, but I can briefly answer it. It's not a jamming attack. It's totally different from jamming attack. The main difference is we're not discarding the packet. We're just holding the packet. And we will, at some point, release the packet. And the server side or the IoT side will receive the message. And there's no alarm, timeout being caused. Okay. Jamming is you jam it, the packet got dropped. And then you have to resend, stuff like that, disconnect, resend. But in our case, in the attack, the packet has never been dropped, but the packet will be delivered at some point. And the other party, the receiver side, does not notice any problem. Okay, so that's the one main difference. How to implement the attack, there's involved a lot of details. Maybe you can contact me offline, and I can send you the other paper. Yeah. take a lot of time to explain the details.
Yeah, thank you. I want to ask how long the delay should be the attack, because you know the IoT slave IoT devices, they report periodically their status to the master device. Yeah. And when for example, actuator close the door, and after it completes the task, it would report the status. So should the delay consider these like? Time?
Yeah, we consider all those factors. We experiment on 50 popular IoT devices. Those are some of the ranges. The short one could be like 10 seconds, the longer one could be 600 seconds. And as I mentioned, some of the Apple devices you can delay to at least 40 minutes or even longer. Yeah. So it depends on the device, depends on their timeout mechanism, keep alive session, and so on. Yeah.
Thank you.
Sure.
Thank you. So thanks Xiaojiang, and thanks everyone for the questions. There are actually more questions online. Maybe Xiaojiang, you can address them like offline, and if you like anyone else want to ask questions, you can talk to the author offline because we are really running behind. Yeah.
Okay. Thank you.
Okay. Thank you. Yeah.